Yeah, we're back with another video. So this video I'll be explaining about the unimolecular nucleophilic substitution. So we're given 2-bromo 2-methyl propane. Yes. And then we're also given methanol. And then there's reflux as the catalyst, which produce ether, Br minus and CH3OH2 plus. Now, without further ado, in step 1, we have the formation of carbocation. So, initially, the bromine atom in the 2-bromo 2-methyl propane, which is a tertiary alkyl halide, will leave 2 electrons from the sigma bond between CBr of 2-bromo 2-methyl propane, which will be pushed toward the Br atom because it is more electronegative than the C atom, which I will show you right here. Ooh, okay, if it allows me to zoom in. I need it. Okay, let me draw an arrow. So it's gonna go here towards the Br atom. So the first step in the SN1 mechanism, it involved the departure of the leaving group, which in this case we have Br atom from the substrate molecule. This will break the covalent bond, which requires energy, and it's usually a relatively slow step, which I've already highlighted right here. So the leaving group, which is the Br minus, will depart from its pair of electrons. It will depart. Goodbye. We say goodbye to Br. Okay? And which gonna leave behind an empty p orbital on the C atom. This generates a tertiary carbocation intermediate. Oh, I forgot. Here it is. Carbocation intermediate. So the carbocation intermediate will be formed and is stabilized by the neighboring metal groups through hyperconjunction, which increases the stability of the carbocation. This stabilization is why tertiary carbocations are favored in SN1 reactions. Moving on to the next step, nucleophilic attack. Okay, so in the second step, a water molecule will act as a nucleophile and attacks the carbocation. The lone pair of electrons on the oxygen atom of water will form a bond with the carbo atom bearing the positive energy. Before I go any further, I've made a mistake, so I will be right back. Okay, I'm back. I actually did not do any mistake, I think. So we should move on. So where did I stop? So in the second step, methanol will act as a nucleophile and attack the carbocation. So the lone pair of electrons on the oxygen atom of the methanol will form a bond with the carbon atom bearing the positive charge, a carbocation. So 2 electrons will be pushed toward the C+. I've drew the arrow right here. Okay, now moving on. The combination of high nucleophilic concentration, the reactivity of the carbocation intermediate, and the stabilizing effects of the solvent contributes to the fast nature of the nucleophilic attack by methanol in SN1 reaction. Fast reaction. Sorry. So this step will generate the intermediate of protonated methanol. So in the last step, which is the deprotonation, so in this step, the protonated methanol will be highly unstable due to its positive charge on the O atom, and will be losing a proton in the H atom to a neighboring water molecule. So not water, methanol molecule. So the methanol will act as a base. Two electrons from no. This is actually not water. This is also OCH3. By the way, I hope I don't make a mistake. So and then so the two electrons from a lone pair of the neighboring methanol molecule will be pushed, and one of the H atoms on the O plus. So the sigma bond between the H and O plus will be broken. Now two electrons from the sigma bond are pushed toward the O atom, since it is more electronegative than the C atom. Yeah, no, H atom. Okay. Then the reactivity of the protonated methanol will contribute to the fast rate of the deprotonation process. I forgot to write it. Let me write it real quick. Okay. So this step will end up generating ether, and then the byproduct is Br minus and also CH3 OH2 plus. That is all from me. Thank you and goodbye.